Hi, my name is Titus Cieslewski, and this paper is about data-efficient decentralized visual SLAM. So, what's the goal that we try to achieve? Single robot visual SLAM is an algorithm that lets a robot create a map and localize itself within that map based on an onboard camera. In multi-robot SLAM, we try to achieve the same with multiple robots. Let's say we have 9 robots moving through the same environment. How can we have them build a consistent global map, in particular in a way that allows robots to localize themselves at places previously seen by other robots? We want to achieve this in a decentralized way, that is, without a central entity that collects all data and represents a bottleneck in computational power, memory, and bandwidth. The main challenge is to achieve place recognition and map optimization among all robots without exchanging too much data. As illustrated here for the case of 3 robots, place recognition and optimization of each robot depend on the trajectory and map data of every other robot. We could simply have all robots exchange all of their data with all other robots, maybe in some compressed form. This, however, would still require a lot of bandwidth and would scale pretty poorly. In particular, the required bandwidth would scale quadratically with the robot count. So in order to minimize the exchange data and to avoid this quadratic complexity, we take a closer look at the main components of Visual SLAM. For each component, we consider state-of-the-art decentralized solutions. These components have previously been shown individually, but not as a full system. We have decentralized visual place recognition, which allows robots to recognize places previously seen by other robots by sending a query to only one, not all other robots, while balancing the computational load necessary among the robots. Then, we have a visual data association method that allows to establish relative poses from matched frames while exchanging a minimum amount of data. And finally, we have a decentralized pose graph optimization method that only exchanges an amount of data that is linear to the amount of relative pose measurements established between the robots. We put these components together and analyze how much each of them contributes to the overall bandwidth requirements of the system. Ideally, this would serve as a reference for further improvement of the components. To analyze the system, we simulate a multi-robot setting on existing publicly available data, here Kitty0, which is split into 10 subtrajectories, 1 per robot. When we look at how much data needs to be exchanged by the system with 10 robots, we can see that a good consistent global map can be achieved with exchanging only around 2 megabytes overall, with some tweaks that we describe in the paper. You can see the contributions of the components at the top right. Finally, the code for this paper is open source and available at the indicated link.